So folks, continuing, we're going to look at this function f of x. And in this case, I'm actually not going to state what f of x is. We're just going to do everything abstractly. We're told that f is positive, and we're asked to give the Riemann sum. So remember, that's R-I-E-M-A-N-N sums to approximate the area beneath the curve f and the x-axis on the interval from 2 to 22. So again, folks, we don't usually worry about what this function actually looks like because we're doing all the manipulation algebraically. But we imagine that there's this function f of x that lives above here, and our goal is to approximate the area between f of x and the x-axis. And we're going to do that with this Riemann sum approximation. So first we're told that we're going to assume all rectangles have equal width. So we can call that delta x. So assuming all rectangles have equal width, and we'll call that width delta x, we can find delta x if we want to approximate the area beneath the curve with 5 rectangles. So let's go ahead and give delta x. Delta x is always b minus a divided by n. Folks, that's not some mysterious formula. That's the entire width of the interval. Right? The width of this interval is 20. How do I get there? I take the b value minus the a value, and then I divide by the number of rectangles that I want to have, and that will give me the width of each rectangle. So this is going to be 22 minus 2 divided by 5, or 20 over 5, or 4 is our delta x. We now want to list out the elements in the partition. So in this case, you can think of it this way. We're going to start at the first element of the partition, 2, and then we're going to add our width to get to the next element in the partition. So that would be 6. If we add the width again, we'd have 10. Adding the width twice more, and then one last time, we get all the elements in the partition. It's worth noting, I think, that we have 5 rectangles, and 5 plus 1 equals 6 elements in the partition. The other thing I want to point out, I think it's important to think about it this way, folks. So we're going to partition this into our 5 widths here. We'll have 1, 2, 3, 4, and 5. This was the first element in the partition, 2. And what we could think of, we know that this is going to be 6, but we could think of that as being 2 plus 1 copy of our delta x. Why? Because what was our delta x here? It was 4, and when you add those together, that does indeed get you to that element there, 6. Likewise, we know that this element in the partition is 10, and we can think of that as being the original starting value, 2, and we're going to add to it 2 copies of our delta x. In that case, we'd have 2 plus 2 times 4, and yep, sure enough, that gives us 10. And I want you to convince yourself, that that's true for each element in the partition. For example, here we have the element 14, and we can think of that as the initial starting value, 2, plus however many copies of the width that we want, which would be 3 delta x. Since delta x is equal to 4, sure enough, that gives me 14. That's going to be important for how we choose to more abstractly represent these in later problems. Okay. The next thing I'm asking you to do is to enumerate the partition. This is because sometimes I want to refer to these, we're always going to refer to this a value here as the 0th element in the partition, and this is the first, and this is the second, up until we get to n. And sometimes I want to refer to them by their place. So rather than talking about the element 10, I want to talk about the second element in the partition. So let's see how that works. Our x of 0 will always be our a value, which in this case is 2. And then our x of 1 is the next element in the partition, which gives us 6. Then x of 2 would be 10. X of 3 would be 14. X of 4 would be 18. And then x sub 5 is equal to 22. And notice I should say, before I write that it's 22, I want to note that that's always going to be the right endpoint of my interval. And in this case is the number 22. I'm doing this here, folks, because in a moment I want to refer to not the element, say, 10, but to the second element in the partition, x of 2. And so I want to show you how we can sometimes enumerate these. The next thing we're asked to do is to list the subintervals of this partition. So let's go ahead and do so. The subintervals would be from 2 to 6, 6 to 10, 10 to 14, 14 to 18, and from 18 to 20. At long last, 18 to 22. At long last, you see, we get what we were kind of after through this whole process. I have now, and if you want to count these, we've got 1, 2, 3, 4, and 5. We've got the 5 intervals that will serve as the base of our rectangles when we think of doing this Riemann sum approximation. So that gives me the 1, 2, and I'm not going to draw them all out, 3, and those will each be my bases for these rectangles that I'm constructing through the Riemann sums. So now let's go ahead and approximate the area beneath the curve f in the x-axis with Riemann sums on the interval 2 to 22. And let's go ahead and start off by using the left endpoint method with 5 rectangles of equal width. So what I'm going to show you now, folks, is the most intuitive way of doing this particular Riemann sum. And my hope is that this kind of grounds you in the idea of using rectangles to approximate areas underneath the curve. But this intuitive way, this expanded way of writing this, is not going to be sufficient for where we're trying to go. So please, as you're learning this, hopefully it makes sense. But what I want you to do is when we move on to the more complicated way of explaining this, but the ultimately more beneficial way of explaining this, I want you to give yourself some flexibility to take on and learn this the next method. But for right now, we're just going to say that the area underneath the curve can be approximated using the left Riemann sum with 5 rectangles of equal width. And so for that, we're going to take and multiply, or we're going to take and compute the areas of a bunch of rectangles. So we'll have the area of rectangle 1 plus the area of rectangle 2 plus the area of rectangle 3, rectangle 4, and rectangle 5. And so as a reminder, our strategy is to do the left endpoint method here. So I'm going to go to where the left endpoint hits the curve, and that's where I'm going to construct that first rectangle, and I'm going to compute the area of that first rectangle right there. Scrolling down, we're going to take the left endpoint of the first interval. Well, I've got my subintervals right here, those subintervals, so the left endpoint is 2. Now what am I going to do with that 2? I'm going to plug that 2 into the function because that gives me this height value right here that I'm going to use as the height of that rectangle. So 2 is not my height, careful there. 2 is not my height, but that's the x-coordinate that I plug into the function to get the height of that first rectangle. Then I'm going to multiply it by that particular rectangle's width. But here we're assuming that these all have equal width, so we can just use that delta x value, which I believe was 4. So we're going to multiply that by 4. So notice that this is I need you to see this as being an area computation. It's a height times a width. Then we're going to take, for the second rectangle, we're going to take some representative point from within this interval. I could use 6 if I'm using the left endpoint method, which I am here, or I could use 10 if I'm using the right endpoint method. I could even use 8, which would be an example of using the midpoint method, but I could actually pick any number inside this interval to use as a representative value of the height of this interval. Okay? So I could pick, for example, 6.5, or I could pick, for example, 8.3 as the representative height, and plug it into the function to get the height of a rectangle. But because I've been tasked specifically with doing the left endpoint method, I'm going to pick 6 there, plug it into the function, evaluate that. That's going to give me the height of this rectangle, and then I'm going to multiply it by its width. Continuing on, we have f of 10 times 4, f of 14 times 4, and f of 18 times 4. Now just do a quick double check, folks. Here's the first rectangle. Here's the fifth rectangle. Notice I have as many rectangles as I'm supposed to have. And for each rectangle, I got the height by taking the left endpoint of its appropriate subinterval and plugging it into the function. Okay, so let's continue now. And now we're going to approximate the area underneath the curve using the right endpoint method. So we'll say that the area is approximated by r of 5, which is equal to, and then I'm going to go back to these subintervals, and now I'm going to take the right endpoint into each one of them. So remember, what I'm constructing is this times 4 plus this times 4, and I'm doing that 5 times over. And that's going to be true for any Riemann sum. I guess I should say as long as we assume that they all have equal widths. If they had different widths, then they'd be their respective widths here. But that's going to be true for any Riemann sum. But we're specifically tasked with doing the right endpoint method. So I'm going to go to the right endpoint of each of these intervals, and that's what's going to get plugged into the function. So 6, 10, and 14, and 18, and 22. And as a reminder, folks, the way I want you to think of this is the height of a rectangle times its width. So in total, that gives me the area of that first rectangle. Area of the second rectangle, area of the third, fourth, fifth. We're adding up the areas of each of these rectangles. Okay, so now let's go ahead and do the midpoint method for this. So again, we're going to approximate the area using Riemann sums, but here I'll use the midpoint Riemann sum with 5 rectangles. And that's going to be, again, same structure as before. And this time, what I'm going to do is I'm going to go and select the midpoint of each one of these intervals. So I can actually, just because I've written out these subintervals, I can determine what that midpoint is just sort of through inspection. But eventually what we want is a systematic way of coming up with that midpoint. So notice that if I wanted to be a little more systematic about this, let's find, say, this midpoint right here. I'll add together the two endpoints, 14 and 18, and I'll average them by dividing by 2. And that does indeed give me 16, which you probably knew just saying what numbers in between 14 and 16 in the middle, or 14 and 18. You probably guessed it was 16 without any work, but there's a little bit more of a systematic way of arriving at that answer 16. So for that fourth rectangle, we would plug in 16, that midpoint right there, into our function to give the height of that particular rectangle, and then we multiply it by its width. So putting in each of these midpoints, we've got 4 and 8 and 12 and 20. Okay. Now folks, in later problems or in more problems, you'll see me I'll actually tell you what f of x is, and you'll actually be able to compute that height, and you would finish out the sum. But that's well, that's an important skill. It's one that stays the same through every single problem, so I'm not going to emphasize that in these examples here. Okay. What I'd like to do now is we want to get a little bit better at doing these Riemann sums. And this was hopefully an intuitive way, and if it's not, please, please, please come by and see me. This was hopefully an intuitive way of imagining these Riemann sums. But we want to start making the notation a little bit more complex, not because we want to make our lives difficult, but because we ultimately want to take limits of Riemann sums as the number of rectangles goes to infinity, and this systematic way of writing out a bunch of f of x times delta x expressions isn't going to be sufficient. Okay, so let's repeat these Riemann sums above, but we're going to use the enumeration of each element in the partition. So here we're going to say that, for example, the area was approximated by our left endpoint method with 5 rectangles. And here what we're going to say is what was, if I go back up to that left endpoint method, what was the number 2 here? That was my x of 0. So this will be f of x of 0 delta x. And you see that if you go all the way up to, let's see here, let's go up to the, this was our first sub-interval. And because we're using the left endpoint method, I wanted the 2. But how did I enumerate the number 2? I called it the x of 0. And then we had plus f of x sub 1 delta x plus f of x of 2 delta x plus f of x of 3 delta x plus f of x of 4 delta x. Now, at this point, I sometimes have students say, wait, why didn't you use f of x of 5? Think about that for just a second. So the answer is, it goes back to our partitions. When we're doing the left endpoint method, I want to use the numbers 2, 6, 10, 14, and 18. And if I look at how I enumerated those, that would be I want x of 0, x of 1, 2, x of 3, x of 4, but I don't want x of 5, because what's x of 5? It's the right endpoint of the last interval, but I'm using the left endpoint method. So that's a reason why I don't use f of x of 5 in this. But the almost simpler reason why I don't is notice how many rectangles I've got. There's my first, second, third, fourth, fifth. Those are the 5 areas of the 5 rectangles that I'm adding up. And so there's no room to add a 6th rectangle because we're only supposed to be adding up 5 rectangles in this process. Okay, so let's do the same thing with the right endpoint method. So for that, we'll use f of x of 1 delta x plus f of x of 2 delta x, etc. And I want you to convince yourself that this is correct. If we go look at our subintervals, when I'm using the right endpoint method, I want these 5 x elements. But the first one that I want is 6, which is x of 1. The next one that I want is 10, which is my x of 2. The last one that I want is 22, which is my x of 5. Notice nowhere did I ever use my x of 0 because that never showed up. That was never the right endpoint of one of my intervals. And so that's why this Riemann sum starts at x of 0 because it's taking the left endpoint of the very first interval, whereas this Riemann sum starts at x of 1 because it's taking the right endpoint of that very first interval. So folks, this method that we just looked at in these first several problems, this method is meant just for intuition. It will not help us with large sums, nor will it teach you what you need to learn eventually about summation notation to be successful in your calculus career. So I hope that this is making sense, this actually writing out these sums of rectangles, but eventually we want to reintroduce the summation notation to try to be able to deal with first larger sums and then eventually limits of sums. So let's take a look at this here, folks. So remember that we learned in a previous pre-work, we learned about the summation operator. It looks like this, the sum, and then we have some f of k, some function that depends on k, and we're going to let k roll through various numbers. It's going to start at some starting value a and stop at some stopping value b. So this is this is called the index. The letter k is the index of the summation. The letter a is the starting value that the index takes on, and the letter b is the stop value. Okay, and then this, folks, don't let this part confuse you. It's just what we do with each index k. So this could be some simple expression, it could be some large expression, it could have variables x in it, it could have variables y in it. It doesn't matter, but it's going to have some counter element k somewhere in it. So this is just some expression involving k. So I want to show you a little bit why we might want to use this summation notation. Here I have this expression here, 40 plus 80 plus 160 plus 320 plus 640. And you might think that there's some sort of pattern in what I'm doing here, and you might want to write this as a concise formula. You would especially want to do this if this had actually not just 1, 2, 3, 4, 5 terms, but maybe 1,000 terms. You would not want to be writing out this long summation. You would want to find a way to shortcut it. So the summation notation allows me to rewrite this. Let's first look for some sort of pattern here, and I don't expect you to see this pattern here, folks, right off the bat. Eventually you'll want to learn how to do this, but that'll be in Calc 2. But I'm going to write this as 5 times 2 to the 3rd power plus 5 times 2 to the 4th power plus 5 times 2 to the 5th power plus 5 times 2 to the 6th power plus 5 times 2 to the 7th power. Now, I don't necessarily expect you to have seen that that's how I could rewrite that, but remember that the number 40 is 5 times 8, and I chose to write 8 as 2 cubed. Similarly, the number 80 is 5 times 16, and I chose to write 16 as 2 to the 4th, and that's how I got these remaining values. Now, this is handy to have written it this way because it helps me then set this up in summation notation a little bit better. I'm going to say what we're adding up is the number 5 times 2 to the kth value. That's what all of the terms in the summation look like. Then I chose to start my counter k in this case at k equals 3 and stop it when I got to k equals 7. So what I'd like you to do is convince yourself that this summation expression right here is just a compact way of writing out this long sum. And you can see that this would be especially helpful if this went out quite a bit further. That would be especially helpful to write this long sum in this compact notation. Now I get it. This is new notation and it is definitely intimidating looking. A lot of students struggle with this notation. So if you're having a hard time learning it, please don't feel bad. But I strongly encourage you to engage with it, keep trying, try to write your own sums, and then come by and see me with questions. I'd be happy to help you with that. Okay. So let's go ahead and practice expanding out this summation notation. Okay. So expanding out this summation notation, let's go ahead and we're going to start our counter at 0. So let's see here. This would be, let's copy the sum first. The sum from n equals 0 to 4 of 3 times n plus 1 to the x of n. And we'll start our counter at 0. So it's going to be 3 times 0 plus 1, x of 0. Plus, then we'll bump our counter up to 1. So it's 3 times 1 plus 1, x of 1. Then we'll bump our counter up to 2. So again, everywhere I see an n in this formula, I'm going to replace the n with a 2. So I get 3 times 2 plus 1, x of 2. Now my counter's at 3, so I'll replace this n with a 3 and this n with a 3. So that's 3 times 3 plus 1, x of 3, plus, and then lastly we get 3 times 4 plus 1, and I've run out of room here, sorry folks, 4 plus 1, x of 4. So if I clean this up a little bit, I end up with 3x naught plus 6x1 plus 9x2 plus, let's see, it's 12x3 plus 15x4, and I've expanded out this sum. Okay? Now, what we will often not do in harder problems, folks, and later on in your math career, is we will usually never expand out sums. It just kind of takes a long time to write them out. So we will have to learn to just manipulate these expressions right here, and that's what's going to be challenging about this summation notation. So my last task for us to do with this problem is to go back to these three Riemann sums. We had these two, and we did the midpoint. I guess I didn't do the midpoint here. So what I'd like to do is go back to these two Riemann sums right here, and I would like to express them not in this expanded form here, which is a fine way to build your intuition, but I want to list them in summation notation. So here we're going to say that our area is approximated by the left Riemann sum with 5 rectangles. Remember, we were doing this for 5 rectangles here. And instead of writing that long expanded expression, we're going to put it into summation form. So we start our counters in Riemann sums in this class. We will always start those counters at 1. And in this case, we're going to make our counter roll up until we get to 5. So this is going to be f of x sub something times my delta x. Now, in this case, because I'm doing the left Riemann sum, remember, and I'm sorry that we have to scroll back up to the previous page, but remember, I did not want to start at x of 1, which is what my counter's at. I want to start at x of 0 here. Why? Because x of 0 referred to the left element of the first subinterval. And so I don't want to start this at x of k, because then when k is 1, this would give me x of 1. I don't want, for my first rectangle, I don't want to use x of 1. I want to use x of 0, so I will put k minus 1 here. Okay? I'm going to erase that, make that just a little easier to read. So that's going to be my f of x of k minus 1 delta x. Okay? So what I need you to learn how to do is how to see this expression right here as the same as this expanded expression right here. And that takes a little bit of practice, folks, and I've got nothing more to teach you on it, and other than to say spend about 15 minutes thinking about this summation notation. What I would recommend doing is actually expanding it out. Let k be 1 and write it out and see what term you get. Then let k be 2 and write it out and see what term you get. And convince yourself that if you do that, you're going to end up with this expression right here. Okay. If we were to do the same thing for the right endpoint method, we'd say that the area is approximated by the right Riemann sum with 5 rectangles, and that's again going to be the sum from k equals 1 to 5, and it's going to again be f of, and we're going to take some value to plug into the function to get the height of this rectangle times delta x. Delta x is the width of the rectangle, and so f times delta x is the area of that rectangle, and we're going to add them up. And in fact, that's how all of these expressions look. It's just that in this case, for the right Riemann sum, I don't want my first value to be x of 0. I want it to be x1, so I just put x of k here. Notice that when k is 1, this is going to read x of 1, which, if we go back up to this expression here, my first rectangle, I wanted to use x of 1 as the value that I plugged into the function to find the height. Why was that? Because when I'm using the right endpoint method, I want to use this endpoint right here, which we've called x of 1. Okay. Finally, folks, I'll go ahead and do the midpoint for this. For the midpoint method with 5, this would be the sum from k equals 1 to 5 still. It's still going to be f of something, delta x. The question will just be, what do I put inside that expression right there? I'm going to scoot this over just a little bit because this expression's a little bit longer. Okay. And how did we find the midpoint before? Remember what we did was we took x of k minus 1 plus x of k, and we divided it by 2. We took the average of the two endpoints of that particular interval. So you can see that back if you go up to here, when I computed this midpoint right here, we took, this was the midpoint for this fourth interval here. I took 14 and I took 18, so I took the two endpoints of that interval and divided by 2. You'll notice that that is precisely what we're doing right here. For the first rectangle, we'll take x of 0 plus x of 1, that's the sum of the two endpoints of that first subinterval, and divide by 2. Okay, folks, what I'd like you to do now is, I think that I've gone through what I need to do for you to learn this basics of summation notation. So please try this potential test question right here. Try it on your own. There is an answer later on in this document that will help you out. But I need you to try this on your own, see what you can do with it, and then check your answer. All right, folks, I will see you in the next video.